Welcome, colleagues. Welcome to the hybrid IAS and to this talk today that we're giving, which is being given by Berit Greinke, whom I'd like to very much welcome as an IAS Residential Fellow. She's come to us from the Institute of Experimental Fashion and Textile Design at the University of the Arts in Berlin. And she's been staying with us already for a short period and is now going to do a work in progress seminar about the project that she's been working on for some time. As I say, I'm going to be handing over to Tinkuta Heinzel and also Rob Seeger, who will be doing a more specific introduction to Berit and their joint collaborative project. But on behalf of the IAS, I really want to say a couple of things. The first one is that when we established the IAS Residential Fellowships a few years ago, we really had a few particular things in mind. The first one was to enable people to come for a slightly longer period to stay at Loughborough to do research work, and really to think of Loughborough as a research destination, a really interesting international research destination. So when we established the month-long fellowships program, we were aware that we would get the potential to have new and expanding international collaborations with project partners from all over the world who think that Loughborough would be a good place in which to establish some work and some research collaboration. But we also hoped that what we could do was to develop, maintain, and deepen some of our extant collaborations and research relationships. And so we were very much hoping that one of the things that the residential program would enable would be people who had been to Loughborough before, were beginning to work with and developing wonderful projects of fantastic international research collaborations with scholars here at Loughborough, but maybe didn't have a possibility of spending that longer time that was going to enable those things to come to some fruition. And we have been totally delighted to see that in our first cohort of international visiting residential fellows at the IAS, we have had colleagues do exactly that. And Berit is one of those. And it's in that context that I really am totally thrilled to welcome Berit today, because Berit came first to the IAS as a visiting fellow for a short period, working with Rob, working with Tinkuta, and developing some of the ideas. They had, of course, a COVID break, like the rest of us in many ways, a bit of a delay and a hiatus. But they have now, with the residential fellowship, been able to start that process again. And they are developing and working on their collaboration toward new and exciting ends. And so this is exactly what this program is for and what the IAS is enabling. And we are very, very thrilled to be part of that. I'm going to tune out and specifically get myself off screen to ensure that I do not cause feedback, but I'm really looking forward to listening to this talk today. And I'm going to hand over to Tinkuta now. Welcome all and enjoy this event.
Thank you, Marcia, for the introduction, for explaining the program the IAS has put in place and which allows us actually to be here. And I'm very happy to introduce Berit Greinke. I don't know where to look now, to the screen or to Berit. I know we know each other, I think, for more than 10 years now. And it was really a pleasure to work with Berit much more closely. And I think, thank you, IAS, for making this possible. Berit Greinke, she's a professor now at the University of Arts in Berlin. And previously she had completed a PhD at Queen Mary in London, have been working for quite a while now in electronic textiles. She's interested in these aspects related to the pleat. And also, she also has interest in the relationship between textiles and sound, which probably also bring us a bit more together in the past. Berit, she's doing a lot of interesting research and experiments related to pleat. And it was also the project we started here with Rob Seeger, to look into this. Probably I'm gonna leave now the floor to Rob as well. We were looking into the way we can work with capacitance sensing, to consider the textiles and wearables as a form of active, I would say, technology. So, Rob, if you want to say something about.
Okay, yes, thank you, Tinkuta. I guess I've known Berit for 8 odd years, maybe. First met her when she was involved with Queen Mary in London with a PhD, and I'd been working for some while trying to look at textile-based antennas and textile-based systems at high frequencies. And so the work she was doing made a lot of sense to me, and as part of the discussions we had, we basically started to say we need to work together. And so finally we started passing comments and information and slowly built up a concept of textile-based sensors and the collaboration between Loughborough and Berlin and ideally 1 or 2 other places. But because of COVID, some of these collaborations have possibly fallen by the wayside. To be fair, this particular visit should have been a couple of years ago, and a lot of things would have been very different, but it's really great to spend a bit more time talking to Berit and seeing what she's doing and where she's going. So she's been working with Loughborough for several years now, remotely, and so on. So it's been really interesting because it's very multidisciplinary, and I found that really, really fascinating how multidisciplinary we can go in terms of technology and in terms of arts and design. So I'm not going to say any more than that because I'm sure Berit would like to get started. So it's over to you now, Berit. So thank you very much.
Does that work?
Oh yes, if you click on the share screen again to bring up your maybe the full one, yeah.
There we go. Yeah, thank you. Hello everyone, and thank you very much, Marisa, Tinkuta, and Rob, for the very kind introduction. Before I begin, I would like to thank the IAS and Loughborough University for hosting and supporting my research, and in particular also say a very big thank you to the IAS team, Marsha, Kieran, Bhavna, and Laura, for putting so much work and care into making me feel welcome and sorting all the practical problems that come with international travel at the moment. So I had a really, really great experience in the last 3 weeks. I would also like to thank you, Tinkuta and Rob, for your support, for your kind support during my stay, and the continued interest and encouragement over the last couple of years. As Rob said, it's been going on for a while, and COVID didn't make it easier. So also to keeping the momentum of the collaboration going despite the 2-year delay. Another quick thank you goes to Bi King, who's technical instructor in textiles, who has been immensely supportive also with her embroidery knowledge during my stay in the last couple of weeks. So today, today's talk has 2 parts, and in the first part I would like to introduce myself and share with you a glimpse into some of the work we are doing at UVK in Berlin. Berlin University of the Arts. I will particularly talk about a collaboration with 4 textile designers, crafters, and e-textile design researchers who have been working with us on folded sensors using various textile techniques such as weaving, pleating, and knitting. And then in the second part, I will introduce the objectives and share some of the work in progress from our collaboration here with the School of Design and Creative Arts and the Wireless Communications Research Group here at Loughborough University. The goal of that collaboration, as Tinkuta already mentioned, is to look into capacitance of electronic textiles, but also looking into the wider implication of how to have people coming from a textile design background working in electromagnetic engineering, which is really interesting and very challenging. So the goal of this collaboration is to make electromagnetic engineering a little bit more accessible for people with no previous prior knowledge in electromagnetic engineering. And to conclude, I will share a few images of embroidered samples, which I had the opportunity and the pleasure to work on in the past 2 weeks in Loughborough. So my name is Berit Greinke. I'm a textile designer and researcher based at Berlin University of the Arts. My research is in textile wearable technology and has a focus on electronic textiles as material practice and tool for artistic expression. So I have become interested and involved in folded electronic textiles during my PhD. That was already mentioned, where I studied how textile crafts may lead to new fabrication methods for soft electromagnetic structures, of which you can see an example here on the slide. One of the practical questions at the time was how to get from here, which is a flat woven sheet of a textile material with conductive traces on, to something like this, which is a three-dimensional structure, electromagnetic structure that responds to the three-dimensionality of the electromagnetic field. And this actually at the time led to a very practical decision of using folds that allowed me to first produce a conductive pattern on a flat sheet using common textile techniques such as embroidery or screen printing, and then to create the three-dimensionality afterwards by folding them up into the required shape. And now, and some years later, I'm teaching in art school, which is a very, very different environment to what I was exposed to at the time. I became really interested by how folding is so widely used and studied in design, mathematics, natural sciences, and engineering. But on the other side, interdisciplinary research collaboration seems to be the exception in this field, despite different research and artistic disciplines often using the same geometries, folding geometries, and even methods and principles to fold them into usable prototypes. So the question that this has led me to is how can co-design between engineering and textile design research communities lead to innovative folded smart textiles and new areas of applications as sort of an overarching questions that lead our interest. But before we go into electromagnetics, I would like to give you an example for how even the collaboration between different textile techniques can lead to new kinds of new knowledge and kind of really interesting and new kind of functional senses. So during a 4-week arts residency at the end of 2020, we worked with 4 textile and fashion designers exploring technologies to design and craft folded dynamic electronic textiles. The focus was on pressure and stretch sensors. So at this point, no electromagnetic function, which they achieved by using knitting, weaving, pleating, and a coating technique for creating prototypes. The results also have just been published online, and the print article will follow later this year. And in the following slides, I would like to show you some of the examples that the residents created. Let me just move this out of the way here so you can see the name. Okay, so Emma Wood, who is a weaver, explored how cherryman can be used to develop naturally finely folded woven sensors. Cherryman is a high twist silk yarn used predominantly in Japanese kimono weaving, traditional kimono weaving. It uses a fiber that is over twisted into a yarn and which subsequently is then coated with sericin, which is the protein that is produced by silkworms. And this locks the twist into place. So once woven, the sericin is removed by boiling the fabric and water, releasing the twist and causing the fabric to shrink. So you can see on the top left, this is what the sample looked like when it came off the loom. And on the bottom left shows what it looks like when it came straight out of the boiling process. And on the right, you can see sort of the setup of the 3-layer system that Emma worked with to create the pressure sensor matrix. So Emma combined multi-layered weaving with this less predictable step of shrinking the fabric, adding electrically conductive yarns to create pressure sensitive micro pleats. And it was really interesting to work with a weaver on this because she has a very, very good eye and a very good understanding for what happens on the small scale of the fabric. So she thinks in yarns, and therefore she was able to produce soft structures that enabled a very high resolution movement sensing matrix. So this swatch, for example, contains 120 pressure sensor points, and we haven't been able to test it yet, but we suspect that it will be quite good in sort of even recognizing very, very small movements. They're also very beautiful, these structures. So here you can see an example of the work of Arantxa Villas, who in her day-to-day practice is working with pleated textiles for costume and textile design. And pleating is actually an ancient craft where fabric is molded in 3-dimensional forms through steam to produce sculptural volume and movement. So the molds are made from paper, so the fabric can be sandwiched between them and steamed to fix the folds. You can see this process on the top left. And it's a process that even today is done by hand. So even planning the patterns, drawing the patterns, folding the paper, everything is made by hand. And there are just a couple of studios left worldwide that are able to do this process. So for example, in the UK, there's a fantastic studio called Cement Pleating in the north of London, who produce very large molds. So this particular sample on the right shows Arantxa's interest in introducing crafts aesthetics into the design of electronic textile. She's also interested in using offcuts and recycle electronic textile materials, as for example shown here on the bottom left. And this pleated sample with a so-called peacock fold pattern has also an embedded sensor matrix where pressure is detected directly on the fold lines when the sample is folded and unfolded. So just like the woven sample, it is constructed from 3 layers and is just held together through the nested folding. And the collaboration with Arantxa was also very, showed how important her experience as a pleater was. To achieve the precision required for the sensors to work reliably and also prevent the folds from shifting. So I also tried a sample like that and it was not working as well as her. So it was really, really needing her expertise in this kind of process. As Sophie Skach explored various knitting techniques, one of which produced bouncy waves that maintained their shape well without elastic yarns. Also here there's a layer principle embedded in the process, making use of the stretch properties of these kinds of knitted structures. The layers were added horizontally in this case, so she couldn't stack them up this way. But as the knitted structure is quite soft and bouncy and actually quite thick, it still works. So even if it's sort of pressured into the supposedly wrong direction, it still catches the pressure of the movement. And with another technique, she created folds that work almost like hinges. So they are knitted hinges, allowing repeatable, precise placement when folding and unfolding the sensor. Pauline Bien, the fourth resident, investigated a do-it-yourself polymerization coating technique to create piezo-resistive materials. Piezo-resistive means pressure sensitive. So this technique was described in a paper published in 2020 under the name of Polysense, and you can see the reference on the bottom by a group of artists and scientists. And the authors describe the process for coating porous materials or structures with a pressure sensitive layer. And as demonstrated by them, this method of sort of reverse engineering materials that are commercially, they do exist, but they're really hard to get hold of. That this really creates a lot of opportunities and design possibilities for textile designers to create new types of sensors and explore different kind of aesthetics also at a low cost. So Pauline was particularly interested in using this combined with shibori, which is a technique of creating patterns through binding and blocking parts of the fabric before submerging it into a dyeing bath. Instead of a textile dye bath, the samples were then stirred in the solution, following the Polysense recipe from this paper, coating only the parts that were exposed. And she built her own little device using an ice cream maker to just keep the solution stirring for more than an hour. So it needs to stir for almost 2 hours. So while this sample wasn't fully functional, it shows quite well how precisely electrical functional areas could be placed using this technique, with the black parts being the piezo-resistive areas. It is also very far from the typical technical textile to visual aesthetics, which makes the process particularly exciting for design. So these were just a couple of the examples that produced hundreds in 4 weeks, and it was very exciting to see. But I would like to have a look now at the creative development processes that the residents also deployed in that collaboration. So despite all the sensors using the same electrical principles, the textile techniques required very different approaches for making these structures. And the residents worked in textile studios just next to each other on the same floor, which is common in research environments and perhaps also learning environments in universities. It's actually quite rare in industry and design studios, where people usually focus on just one textile technique. So over this short period of 4 weeks, we observed 3 ways of how residents made sense of sensors in the making and exchange process. So the technique interpretations describes how they use the knowledge in their respective techniques where they were specialists in to come up with possible solutions for the same problem. So this occurred in various ways. So for example, while some woven and knitted folds were similar in final appearance, the textile characteristics such as stretchability bring different opportunities for integrating these sensors into these various tangible interfaces. And the impact on the treatment of the raw materials was shown through the polymerization process, transforming the functionality of conventional non-conductive fibers. So this extends really the possibility to design for specific aesthetics and sensory outcomes based on textile rather than on electronic function. As mentioned, the residents worked side by side, close together, which also allowed them to have a continuous exchange. In addition to discussing their results, they also passed on textiles to be used as examples or processed further with different techniques. So this was specifically the case for pleating and polymerization, as these processes could be applied after samples had been woven or knitted. So the combination of these techniques envisions customized folds and personalized designs that extend conventional sensor fabrication methods. So this is an example, for example, that was knitted by Sophie and then passed on to Pauline, who polymerized it, who first felted it and then polymerized it afterwards. While most material applications relied on the controlled processes of the respective designers to achieve optimal results, chance was also a great factor for some of the samples. So using a single technique did not always lead to the desired function, as we all know, and research things go wrong and so on. So such results usually are being deemed failed experiments. However, passing on and processing the samples further often lead to interesting new ways of making senses through combining techniques and then overcoming restrictions occurring when using just a single technique. So for example, weaving could be seen as restricted to the perpendicular direction of the warp and the weft, while the knitting machine produces a weft-based fabric surface. The experiments and comparison of the different fold designs opened new directions for movement and allowed the weaver, knitter, pleater, and polymerizer the possibility to also plan for an added dimension in their design. So the example shown here is a woven sample where the design did not work out in the vertical layout of the woven layers. The weaver then passed the sample on to the pleater, resulting in a different layout that created new contact and pressure points when folding the sample on a slightly larger scale. So finishing the first part of my presentation, staying with folds, but moving on to electromagnetic functionality, I would like to briefly map out the collaboration with colleagues here, especially Tinhuta and Rob at Loughborough University. So the design process of textile antennas and capacitive sensors is actually similar to the one of standard printed circuit board components. But interesting to see is that while the textile design community is very active and makes a lot of contributions in the field of electronic textiles, contributions to electromagnetic engineering, however, are actually quite rare. And I believe there are a couple of reasons for that. So while the process of designing and prototyping might be similar, due to the use of textile materials as sort of non-standardized electromagnetic materials, it is absolutely not the same. So when applying non-standard materials, additional steps of material selection are needed and electromagnetic material characterization is necessary. These are often, from my own experience, error-prone, particularly in the case of textile materials, which are thin, porous, irregular, and most difficult of all, they just move a lot. So this makes them difficult to measure with sufficient precision and achieve repeatable results, which are really needed in this kind of process. Due to these difficulties, textiles in electromagnetic research are often locked into place during measurements, like shown in this image. We built a sample holder to, have it in the right angle and make it not move, or are even replaced by flexible non-fibrous materials such as leather or coated flexible films. This, in my opinion, can lead to narrow selections of textile substrates in electromagnetic engineering, and it also often contradicts the reasons why textiles have been chosen in the first place, which is that they are thin, porous, irregular, and move around a lot. Another barrier is the test equipment for more advanced electromagnetic designs is very expensive and specialized. So for example, on the left, you can see an image of a typical antennas measurement lab with chambers built for specific frequency measurements and network analyzers, which costs like tens of thousands of pounds or euros. And on the right, this is a very typical setup in our design research environments where mostly low-cost equipment such as Arduino microcontrollers are used, which gives us some ideas, but are quite limited in evaluating electromagnetic properties. And in addition to this, retrieval methods for electromagnetic parameters are mathematically very complex and software tools are not readily accessible outside of engineering research environments. So that's actually also a problem that we frequently encountered in our collaboration with us in Berlin, not having these types of software, having no access, not being able to do some of these processes ourselves. So coming back to our original question, how can co-design between engineering and textile design research lead to innovative folded smart textiles and new areas of applications? And this is my only slide with a lot of text. I'm sorry. So our goal is to develop an accessible toolkit for the simulation, fabrication, and characterization of electromagnetic textiles for microwave applications. And addressing the specific challenges when designing antennas and electromagnetic-based sensors, the goal is to enable textile researchers to implement and analyze designs for this frequency band, creating possibilities of designing electromagnetic applications without expensive equipment and encountering the problems that we just talked through. We believe that by instilling a textile practice and employing the skill of textile designers in electromagnetic engineering, the range of high textile quality structures in antennas and EM-based sensors will increase. And the first step of this, get together people from electronic textile design and electromagnetic engineering communities will actually happen next week in Berlin. And where we co-organize a symposium with interdisciplinary talks and hands-on workshops. So it was something also that was supposed to happen 2 years ago. So we have a delay of 2 years, but we're happy that it finally can take place. So just to conclude this presentation, I would like to share a few images of the embroidered samples I have worked on in the past 2 weeks. And I was able to use this digital embroidery machine in the lab of the Wireless Communications Group in Walthamstow, where Rob is based, and also the embroidery software facilities in the School of Design and Creative Arts. And the two buildings are on the opposite side of the campus, so it was like a daily commute. So for now, I just looked into the mechanical behavior of these embroidered samples, varying the pattern size and stitch layout. So I spent quite a bit of time just producing samples, taking them, back to Berlin later on, and having a look at them in more detail. I became really interested in using a lace embroidery technique, which combines a soft net structure, which you can see on the sort of where the fold is happening, together with the more rigid areas that keep the folds in place. And together these form the fold patterns and also the tactile properties. So they have a really interesting also tactile feel to them. And just yesterday, and this is very much work in progress, I also start to include conductive patches that are insulated by the embroidery thread. So while this is certainly only a start for also getting back into our project and into this kind of research after such a long time, spending the time in Loughborough in an engineering environment has been immensely helpful to start thinking about these kinds of structures again. So I really look forward to the next steps and would like to thank everyone for listening.